Hey, what's up? I'm Stefan, and I'm the organizer and host of the emBO++, the next level conference for embedded software developers. The talk you're about to see is about generic programming with TypeExpert by Rémi Drolet. It was recorded at the emBO 2021, and thanks to Leica Geosystems, you could check out this talk for free.
My name is Rémi Drolet. I'm a software developer at Imagine 4D in Montreal, Canada. So it's it's quite far away from Germany. So I want to talk about my template meta programming library that I wrote just before COVID, and then since then I expanded. Then I discovered 3D printing, so I had another hobby. But I took an interest in template metaprogramming mostly because I wanted to understand how it worked, how to start my how to develop using this tool, and I discovered firstly MP11, and then Kvasir.mpl. I will screw up that name all during all the presentation because it's I'm sorry. But I discovered Kvasir.mpl, which, as you know, it was developed by Chiel and Adno. So I found some. There were. It was an extremely good library, but I wanted some. I wanted a little bit more power or expressionability to this library because I encountered some edge case where I needed to modify the function, and that was quite something to behold. So I wanted to create a new library just to see if it worked, and it wasn't supposed to succeed, but it failed in that regard. So I created TypeExpert because it's a type expression, and it allowed me to have the namespace TE, which is like type name T. Well, not my best pun, but it's my library. So let's begin. So first, a disclaimer. Um, go. So type-based TMP is a complex subject. It's not SFINE, it's not ContextPer. It's what you can use to make those two, SFINE and ContextPer, and I guess concept in C++20. But it's not the same thing as those two. Not even consteval. Type-based TMP is basically you play with types. You start with an int and then you have an int pointer, for example. This is type-based type-based meta function. std add pointer. It add a pointer. So I made a library as a remake of Savea.mpl, and I mostly want to show you how to read and write it, not how to use it. For example, I will not show you how to create, to take a tuple and then, no, sorry. I will show you how to write something to take a tuple and then sort the types by size, I guess, something like that. But I will not show you how to integrate this into your code so that you can use it at runtime. I will just show you the template part, and then you can do your own stuff mostly. So I may be fast to explain, and that's the problem because it's TMP. It's not a very common interface, and you may be a little bit not confused, just you're not used to this kind of syntax. So I will just go into each function, say what it does, and I hope that you just buckle up and follow along. So, and also there's the equal operator. I will use it as a static assert is same left and right part. So if you see a equal, it's mostly because it compiles. Okay, so this is a disclaimer, and we can start. Okay, so let's start strong. So basically, the problem that I have with alias.mpl was that it has variadic inputs, but the functions are all nested together. So for example, if I want to do a composition of function f, then you do g with some arguments, whatever the arguments, and then you do h, so f then g with arguments h. You need to basically call, and then you nest together the function. So f contains g, and then which contain the arguments, and I'll explain this part just after. And then you do h, and then at this point you don't need to do anything else. But if you want a generic function that can continue, you have to basically have like this empty bracket that contains a hidden meta function. And this, the first types of call is the big nested meta function. And what basically call, take the TS that is there at the end, all those variadic inputs, and put it inside of F. Now at this point, it becomes the responsibility of F to call the next meta function. So it will call G, that will use the arguments as an argument. But it must, the argument can also be a meta function, a meta closure in this case, because it must end. Like I don't have a good example, but if you want to see if it's an int, well, it can be an int, and you can check if it's true or not. The point is that the meta closure can continue indefinitely, and this is why we have those empty brackets. They contain an empty, not an empty. They contain a default meta closure named identity or listify. It depends on the function, and you can use, and then the functions call the next one with the result. So this is why at this point the arguments are finished, and you call h next. So also the next meta function is always the last template argument. So this creates two things: those empty brackets that are just there because they need to end, and this trailing of angle brackets that are just there to close the nesting. So for example, in this meta function that I call add pointer cons, just to make something generic, in Xavea you'll have to do call add pointer add cons add pointer add cons. You end the function. You have all those trailing nested angle bracket, and then you put the input that is template there. So if you say add ppcp int is equal to int pointer cons, because each time you send the result to the next meta function, meta closure. So it's become the responsibility, like I said, it's become the responsibility of each meta closure to call the next meta closure. So the way it does it is, as you can see, add cons. You have this typename C, which is the continuation, the next function, and all meta closure contain this alias F templated with the input basically. So this T is the input, and you call it like that, which is not very pretty, but there's some function to simplify how to write it and how to use the type traits, basically with templates. So now if you had cons, we say typename C template F cons T. So the next function, which is C, receive cons T, and then the next one and the next one does the same thing. So yeah, that's the basic of Xavea. And basically the problem that I encountered was the source of it was basically this C at this point, because C is just the amalgamation of all the other meta function. So for the first add pointer, it's C, is the rest of the function, like add pointer, add cons, add pointer, add cons. So if I want to do this operation and then do something else, I need to go inside this meta function, take the last argument, go into this meta function, take the last argument, and etc. It's possible, but just not very pretty. So yeah, so I wanted to create my own library to solve that. So it started as an experiment. I wasn't supposed to succeed, and I didn't want to have a lot of angle bracket. I also wanted to compile on every C++11 compiler, which basically I just need the variadic templates. Yeah, just the variadic templates. Once you have it, should work. And my way of testing is going into Compiler Explorer and just changing every single compiler up to the end, all those that compile with C++11. And if it worked, hey, it's perfect. So I also wanted, as with MP11 and Kvasir, I wanted to have a simple way to use the standard stud type traits library. There was some things I wanted to improve with plus minus, basically the operators. And this is the big thing. This is the big thing. I wanted variadic meta function. And using those meta function, I wanted to use basically I wanted the triple dot to use them within the function. So, and as a result of that, I could write basically my function right, which is the most powerful meta function I ever wrote. I'll explain that at the end, because to be able to write, you have to read first. Not my best pun, but it worked. Okay, so let's start the presentation of my library. So, like Kvasir, if I want to do a f then g with some arguments, then h, well, I eval pipe f then g arguments and then h. That's it. There's no nesting except the argument with in g's, but that's part of the deal with arguments of g. So, and I want a simpler implementation of my meta function that I call meta expression. So basically, except the fact that I use a f, but there's no continuation of the next function. I only use, well, I have this f, and then the type of this f is const t. It looks simple. It's not. It's a little bit more complex than what you're used to with the standard meta function, but it's pretty much it's very similar. So, and if I want to do this pointer const, in my case, it's eval pipe ts of input. I need to explain what is ts. I'll do it later. And after that, just a schema separated templates arguments of those meta expression. So add pointer, add cons, add pointer, add cons. Just to be sure, this is not the stud version of those of this add cons and add pointer. So yeah, it looks pretty. There's only 4 angle brackets in there. That's a win for me. So add ppc int is in pointer cons. But how is it possible? Okay, so you need to understand a few things, not much, just what I'm referring to when I call what is a meta function, what is a meta expression, what is TS that I said I want to explain, and then this thing that is eval pipe, because it doesn't take a T's but ES, but E's expression basically. So first of all, eval pipe. Well, I'll just put at the bottom of the screen just a function so that we can refer to what it is when I talk about it. So let's start. So a type list. Type list is basically just a variadic template on a struct. This is the most basic one, and yeah, that's basically it. That's just a type list that can add 0 or an infinite amount of types. It can be represented with templates it can be represented with templates in either a definition or a specialization. So basically, if you have template type name ... f, you can write my tt std vector without any arguments. It's not std vector of int, just std vector. Or tuple, same thing. But the thing you have to know is that other types like std, integer, sequence is not the type list, because it's the function signature that I call is template type name t small caps t. And those t dot dot dots are values, not types. So std integer sequence is not a type list. It's not a very it's not a huge deal because we have ways to represent it as a series of integral constant, stud integral constant. But I have like a function that transforms those type lists of stud integral constant to an std integer sequence. Remember that I want it to be compatible with C++11, and C++11 doesn't have std integer sequence. So also, the reason I want to call it this TS TS is because, well, that's the default of what I call it. It's type name TS. Okay, so a meta function. You already know those if you are familiar with stud type traits. It's basically any class that have a public internal type def named type. So you can have access to this result with type name, function name t, colon type. It's quite simple, but it's become tedious to write it, so we have alias to it most of the time, so that we append underscore t to alias it. So a typical meta function is template type name t at cons using type it equal to cons t. So you have an alias that is type. But this at cons is not the same that I use here because it wouldn't work. Because I cannot have like a add cons and then nothing because I want to send it something. It will become more obvious on the next slide. So a meta expression, this is what I call my the thing I want to interact with. Kvasir has basically it's a meta closure, which is an f, an alias named f, a template alias named f. MP11 have this same thing but with q. It's just named q. Me, it's a little bit different. It's basically a meta expression is just something. It's just a class that contains a meta function named f. Yeah, I use the same f. If Odin or Chiel want to me to name it something else, I'll do it. Not a big deal. But as long as it's the same name everywhere, I can use it. So add const, this is just a simple struct that is named add const. It have an internal class named f that is templated, and I use it with a type inside, with the result inside an alias named type. So that worked. So the problem is how do you access this result? So you have to say result. You have to say type name e, which is this add cons, template f bracket t, then type. Obviously, I don't want anyone to write this. It's tedious and not very useful. So if I can automate that, it's a win. It's very similar to a functor or lambda, but for TNT. So if I could name it nothing, I will do it because I want to do the same thing as like the call operator. And the reason there's a template there is only because the parser have some trouble before to distinguish between a type and a value. It's a detail, but you have unfortunately you have to write type template. Sorry. Okay. To avoid something that I call that is called the alias flaw, this f is not a template. This allows me to be compatible with every single compiler at the cost of having to write type basically everywhere. So to convert a meta function to a meta expression, you rename it f, and then you wrap it with your name of the function. That's all I did to convert add-cons to this meta expression. Or you can use wrap type or wrap, but it depends if it's an alias or not. If it's, for example, type traits, yes, stood add-cons, you have to wrap to have the result. I have to wrap it and then get the type. So that's why I call it wrap type. And wrap std add-cons t, immediately that I wrap it, the type int, it will immediately get the int pointer. So if I get the type, it will not, int pointer doesn't contain the type. Okay, next slide. So TS, this is the function that most of my that most of my evaluation begins with, because it's a typeless meta function and a meta expression all at the same time. So it's TS type name dot TS. So it's a typeless type. This is a using type is equal to itself. So it's a meta function, but I don't use it that much. Sometimes it's useful, but not a whole lot of time. And here, this is where it gets interesting. It's templated to dot dot dot, so it's completely ignored, and the struct f have a type that is TS of the original TS there, the original types that are there. So basically, once I evaluate it, it ignores what it receives to continue with the original template. So for example, type name TS int double template blah 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 f float, you get the answer, it's TS int double. That seems very obvious or very not useful, but it's actually insane. There's a specialization for one type, so that basically TS int template f float type, well, it ignore the float, so it's only output int. And the reason there's a specialization for only one type is that as a result of something, I cannot have multiple types, and I can only have one. And if it's wrapped inside a TS, I can use it somewhere else. So yeah, that's basically it. So when I say eval the pipe and TS, it basically says in yours whatever you receive and continue with int. So I know that the add pointer that is there will receive a int. I didn't define how I can pass this result to the next function. I'll do it in the next slides, basically. But that's why there's a lot of meta function meta expression that begins with TS, because it starts something. It ignore the fact that it just ignoring everything, continue with what is inside. Okay, eval pipe. Now this is the big thing. It's just an alias. It's an alias to pipe ES, so everything inside it is a meta expression. Template F and nothing. That's interesting. So basically, once I said eval pipe, it will alias to pipe all the meta expression, send nothing inside it, and then TS will receive nothing and continue with int. That's useful. So so basically, eval pipe is here's a list of function and evaluate it, and pipe is just the list of function naked in the open, is just waiting to be evaluated. Okay, so basically pipe, how it's implemented. It's basically just a fold of expression. So if you know fold left, you can, which is basically a stud accumulate in the standard library, but in template metaprogramming, so it's a lot more complex, and I don't want to show it to to everyone because it's just a big pile of type name everywhere and templates. So just know that I migrate this code to template to a template library to template form, and instead of having a value, like for example in accumulate, you can send it the binary functor plus, for example, and what the fold left will take is it takes the first two values, do something which output a result, take the next thing in the list, and do the same thing again, output a result, and etc. Now the problem is that I don't have any values. I only have expression. They are there, but they don't contain. They are not. I'm not able to pass it an, inputs arguments. So this is a bad pseudocode. Just to show you my point is that I have this type name E1 and E2, those two expression. I want to evaluate them, but I can't because there's no input nowhere in this functor. Yes, in this meta function, in this meta functor. So I cannot use it. So I just cannot send the result to the next one. And the solution for this, use TS. Okay, this is the actual implementation of my functor in the fold machine. So I call it type context. And basically, if you have a type and an expression, you can simply send the type to the expression and evaluate it. So type name E, template F, T, and then it gets evaluated. So if E is add pointer, it will receive, let's say, an int, and it get in pointer. But if it's TS, which as you remember, is a meta expression that completely ignores what it received to output what is there. What is there? Well, I will simply call type name E template F with the TS, not the TS of TS. Yeah, maybe. It's just the types, with only the type inside the F. And then I continue doing it. So this is useful. TS is useful because it's safe to ignore what it receives. So I know that because I created it. And so in the case of, for example, eval pipe, TS of int, this will be TS. It will go here, and it will send to add pointer only the int. So it will int pointer. But int pointer, since it's a type and not TS, it will go there and continue the evaluation. So I can now use variadic meta expression because I'm only folding them to get a result. And so I can finally have variadic meta expression. So TS of int and pointer is static assert is same as const in pointer. And if I have a special meta function that I name, well, very originally transform, TS of int float that I send to transform. Transform basically is a for each. Will add a pointer, add a const to each of them, and output a TS. So TS of const in pointer, and now the only problem that my meta function meta expression needs to deal with is that they may output a TS because it's both a meta function and an output, and I can parse it correctly. So now let's see if you if you have followed correctly. Oh yeah, I almost forgot. Pipe is implemented exactly like what it expect. So you can say you can have an alias meta expression of add ppcpc is equal to pipe not evaluated, add pointer, add const, pointer const, and then I can evaluate it. This alias is immediately transformed into this series of meta expression, and it will output the correct output, the correct answer. And so and that's because pipe is implemented exactly like what like the meta expression it expects. Next. Okay, half time, perfect. So let's see if you follow. So what is the result of ts of int? In this case, it's pretty easy. It's just ts that output an int, so it's int. Ts of nothing. What is that? Well, since ts is variadic, it will output itself. This is basically a nothing. My nothing is basically just a function that output nothing. In the case of ts, int, and float, well, you already seen it. It's int, ts of int and float. Just to be sure that you understand ts. Int string, ts of float. So the first ts will output int and string, which will be received by ts, and then it will completely ignore it and just output float. So it's float. Okay, now it's a little bit more of a corner case, but ts of int. Well, it's one type, so I can output it as ts of int. I don't want the ts to be recursive too much, so it's ts of int. Ts of int, pipe, ts of float. Notice that the second ts is inside the pipe, so pipe will just receive an int, output it to ts of float, which will completely ignore int and just output float, so it's float. And finally, ts of nothing, pipe of nothing. Well, it's output for very obvious reason that since pipe will see that there's no function to output, it will simply output, and since there's nothing to evaluate to, it will simply output what it receives. So it's ts of nothing. Okay, so now I will describe some useful meta function that is not just some corner case of what I wanted to write. So basically, identity would receive something and output it. It's identity. It doesn't do much on its own. It will output it in the TS. Just to be clear. Wrap, we already talked about it. It will just take an int and wrap it into a stud vector. This will output a stud vector of int. I didn't show the std allocator of int, the ident. How do we call it already? I forgot. Sorry, I'm too into metaprogramming. The allocator, yeah, the allocator. So eval. So next is wrap type, which basically I already talked about. You std add pointer will receive an int, and I will get the type next. So it will be int pointer. So with an alias, we don't need to get the type. So it's std add pointer t. It will output int pointer. Okay, at is very useful to just get me the type at this index. So in the case of int float double at 0, because obviously index start at 0, it will take the first. But the cool thing about at is that I make sure that it work with the negative number, and with -1 it start at the end. So at -1 it's double, and -2 will be float, -3 will be int, and in both cases they will wrap around once they go beyond the end. So for example, at of 3, 0, 1, 2, 3. And the same thing on the other side. So -4 will be double, etc. Now this is something that I found very useful because I use it everywhere on my test. In my test, is same as. So eval pipe ts int float. I want to check if it's the same as int and float, and it will output a stud integral constant of bool true. And I know that there's at least like 2% in this world that will be very jealous of that, because the other same as, if you want to do something that continues and then use it as like a meta expression, you have to listify in Kvasir at least. You have to listify the result and then check if you have to check if one type is equal to the other. But me, it's variadic. I can just use it like, here's a list of type, check, look at if it's the same as this list of type. And it worked. So now I can use it with everyone inside my assert and my test case and da da da. Finally, flatten. Flatten is a little bit more, not much complex, but it's basically like you have this, you have a TS that will output TS in float, TS int, and then float. So from here to here, it's inside this TS. And flatten will just take the types that are inside the TS and flatten it. So there's no more TS there. It will say, it will output int float, But if you flatten, it's only on one level. So if you have a TS of TS of TS, it will output like just a TS of TS. If you, I hope you follow along on that, but it's only on one level of flattening. I describe this as a necessary evil because sometimes in the algorithm that you use, basically you have to flatten it. Okay, the next three functions are what I call my three musketeer, basically transform, which for each types inside the TS, int and float, you have a variadic function, you have a variadic expression that will, in this case, add to pointer. So int pointer pointer, float pointer pointer. It's a for each, work as intended. Fork is a little bit more complex, but not that much. So fork have a list of meta expression, and each of them will receive all the inputs. So in the case of of TS in float, fork wrap type is same, will receive int and float, which will output bool constant false because int and float are not the same. At 0 will receive int and float. Look at what is the first. It will see that it's float. It will see that it's int, and then just output it. And transform add pointer will just take the two, take both, and just add a pointer to both of them, and then wrap it inside the TS. So the output is TS, bool constant false, int, TS, int pointer, float pointer. Each is the least useful one, but it's basically an optimization of basically you have to have the same number of inputs and meta expression, and basically the first input will go into the first expression, meta expression, the second input will go into the second meta expression, etc. So in the case of TS in float double each, it's very badly named, I know. Each add pointer, add cons, same as double. So int will go into add pointer, float will go into add cons, double will go into same as double. So the result is int pointer, cons float, and bool true, basically. Okay, now for the operation on numbers and sequence, I provide two alias, basically E and B, for integral constant of int and integral constant of bool. All those natural operators like plus, minus, multiply, divide, modulo, less equal, etc. I make sure that they work in two form. If there's nothing inside the plus, inside the meta function, the bracket, it will receive two inputs and do the thing, which is in this case plus, in order. But if you only put one types inside of plus, it will accept one inputs basically. So it will say TS E4 plus E2 is equal to E6, obviously. And in the case of E4, E2, you plus them, and then again it's E6. No, not E. Sorry, it's my French. I. Okay. For std integral sequence, I said that we cannot use it as a to manipulate the values inside, we cannot because they are not types. So what we have to do is convert them into TS of E0, E1. So I want a list of types from 0 to n-1. So that's exactly what mexsec does, mex sequence. So mex sequence of E3, 0, 1, 2. But again, if you have an empty mex sequence and you send it E3, it will do the same thing, 0, 1, 2. So now I want another useful method function is zip index, where you zip it with the index. So in float, zip index, the output is TS of TS E0 int, because int is the first, so it's index 0, and TS E1 float. Float is the second one, so it gets the index 1.
Wir sind hier in einem kleineren Grossraumbüro.
Bei den Leitern habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Leica Chiel Systems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge in my life hobby with my office job.
Das Besondere an der Leica Chiel System ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
So, for example, this is a little bit more complex as a meta expression, but I want to evaluate TS of int float int. I want a zip index. Okay, so at this point I have int float int, and then with the zip index I have basically every single type with its index. I want to only keep them if the second one, which is the type, is the same as int. So at this point I remove this float because the two others are int, and I'm left with TS of E0 int, TS of E2 int. And then I transform it and just take the first because I want to just get the index of all the ints. So TS E0, E2. Then I have another meta function that just convert it to a stud make sequence. And that's it. That's how you, for example, you take a tuple, you need to unpack it first, but that's pretty simple. And then you just, if you want the index of all the ints, you can just copy that. And also, this is like a pretty common way for me to write my code, because if I'm debugging and I just want to remove a function, I can take this line and just add the comments, and it will remove it. And that's very useful. Because in Kvasir, since everything is nested together, you have to comment the first bracket and then and all the meta function, and then the second one, and it gets very confusing very fast. Comment the line. Okay, so I have a couple of meta functions for type list manipulation. Basically, everything you expect from the stud meta function from the stud library, basically. So keep it is a filter, remove if, we already know what it is. Partition, which basically is a fork of keep if and remove if. Cartesian is basically it receives two lists and put together each one of them like so. Like if it's receive A, B, and the second list is T1, T2, it will go A, T1, A, T2, B, T1, B, T2. Sort is sort. It take a binary predicate and just sort them. Group range is interesting because it's basically every types that with with a unary function output the same output, it will group them together. So basically, that as a quick example, I just said, okay, so all the A's are together. B is alone in this case. C and C, and etc. And now, if I want to make something to only takes I want to take a range and uniques it to just retrieve all the types but only one time. Well, it's basically, this is actually the implementation. I just have to group range with nothing, so it will output all the same in the same group. And then I take the first for each group. For each group, I take the first. So this will take the first A and just put it inside the list. And that's my implementation of unique. I'm quite proud of this one. It's quite good. It's quite good, I think. Okay. Now for the new things in my library. I have 20 minutes. Arthur Dwyer did a blog on basically how do you do the same operation on some template metaprogramming library, and they all have the same problem, which is basically that in the case of on a type list, you want to remove that the types are empty. You use a predicate and sort them by their size in decreasing order, and rewrap it inside the original type list. Only MP11 and Anna was able to do it, but MP11 doesn't have continuation or composition in my case. And Anna is a whole nother beast that I don't want to get into. But the problem is that this is a Kvasir MPL library. The Kvasir MPL way to solve this problem is that you start with std tuple of int empty class int2. So you unpack the tuple, so you only have empty class. You remove those that are empty. You sort them by this predicate that is there, blah, blah, blah. And then, and that's the problem, you wrap it inside tuple. That's not very good, because if I change this original, if I change the inputs to variant, it will again unpack it, remove all types that are empty, then sort and sort them, and then it will wrap them inside tuple. That's a big problem because that's not the original type list. The answer is in this case it's a std tuple of int to int. But the problem is that the function contains a dependency on its type, and I wanted to solve that. So this is my solution. A function that I name onArgs. I'm not very imaginative. So basically on the arguments, I want to do nothing if it's basically anything else than a type list. So this is very generic. It doesn't do anything. It just output the same thing that it receive. But in the case that it's a type list, so I can specialize it with this template class f, then the templates arguments of the template. That's a lot of template. So if it's this f of ts, I will evaluate basically a new evaluation of the inputs, which is a ts. I forgot to change it, but it's a ts. Do the thing that you want to do with it, and then rewrap it with f. And I can do that because this f is accessible from here. So I'm creating a new meta function depending on the input. So now what I can do with it is, well, basically put it inside a for each. So this is my meta function. So onArgs, remove it if it's empty. Sort them. It's a binary predicate, so it receives two types. I will transform each of them by their size, and then I send it to the greater predicate. So greater will receive two types because it's an operator, and I said that if it's empty and it receives two types, it do the thing. And yeah, that's the meta function, meta expression, sorry. And now I'll test with two type lists at the same time. So eval pipe TS of a tuple and a variant with E as an empty class. I will transform and apply this meta expression to both of the inputs, and I'll check if the result is the same as a tuple of int for 3, 2, 1 and a variant. Sorry, 3, 2, 1, and yeah, it worked. This is one of my most important tests. I also have the solution for Eric Nibbler's tuple concatenation as one of my most important tests, and I made it work, but it's a little bit more complex. I don't want to show it in this presentation. Okay, so now the new variadic function. Okay, so if you want to use ... inside a meta expression, you need a variadic template. So in the case of summation, for example, int ... e, so you use the values of int. I can eval pipe ts starting at 0 plus e, and then the templated int ... And it's not the e that is ... it's the plus. So the plus will get expanded with as long as you as long as you write basically any numbers inside this summation. So so if you have no ints inside of it, you will output 0. But if you add more ints, it will do the summation, because that's what it does. Swizzle is something that is useful in video game development, where you just rearrange the inputs by index. So same thing, you just fork and you get the index. So it will copy, each at will receive all of the inputs and then just take the one that is important to them. Okay, and now it's getting very interesting. Copy. I realized at some point that copy, you can do something like, okay, I'll use an n and then decrement this n and then just append the same inputs to itself. And then I realized, hey, technically, if I write a fork with as much identity as n, it will technically copy and then just use it as just output it as it is, since it's identity, and it will work. The only problem is I don't know how much n I need to write. So why don't I use my library to write it for me? So copy is a eval pipe of make sequence. This is not supposed to be that. Okay, replace this e with n. With replace the size of with I of n. Transform identity. So now I start with all a sequence of integer constant, and I immediately change them each of them for identity. I can do that because it's type, it's not values. So I have a lot of identities, and then I wrap it with fork, and that's it, and it worked. I'm quite proud of this one, but the next one is even more incredible. So basically, template unsigned n with basically a meta expression with a repeat, because I want to repeat the same function. So what did I do? Well, I take this expression and I copy it n time, and then since it's a list of type expression, I need to flatten it to remove those ts that are outputted by this copy. And then I wrap it with pipe. So now I inherit from pipe es ... es ... Those es are repeated n times, basically. And now my most useful meta function, write. So write is possible, is technically possible with other libraries like Kvasir, but you have to nest things in and out. It gets confusing very rapidly. And in my case, I just wanted to do a write. So okay, so it's difficult to explain very rapidly, very simply. But basically, I take the inputs, I create a method expression with those inputs, and then I evaluate it with those inputs. And that's basically what I do. Write takes something that will and it takes a series of meta expression that will create another meta expression and then evaluate it. It's better with an example, but it's extremely powerful. It's basically, technically, I can write any meta expression with basically my arguments. So I'll take a quite simple example, which is keep if. So keep if, when you think about it, what is keep if? Keep if is you have a list of types, and you just want to remove those that the predicate is not true. So the way you can do it with my library is write null is basically just you start with nothing. You start with no inputs, but you create something you create the meta expression with those inputs. So basically, I said so for now we have all the inputs. We transform each of them with the condition that if the predicate is true, we will wrap it inside append, and if not, identity. So in the case of ts int float double, keep if not same as float. So we want to keep if it's not the same as float. So we only want to keep int and double. This keep if gets transformed into type of ts nothing append int, because the int, since it's not a float, it will get wrapped inside append, and the float that is next will get transformed into an identity, and then the double will get wrapped into an append, and then I evaluate this. And since I start with an empty list, I append int, I do nothing in case of float, and I append double, it gets the result that I want. It's quite something to wrap your head around this function. And as a finally, binding. Binding is basically I want to just do an operation on one of those inputs. Well, basically I can replace it with each identity, a list of identities with only the one at the index described here with the function that I want to do. So basically what I do is I create a list of integral constant, change each of them with identity, except the one at the index where I replace it with the list of function. And then it worked. I just said, okay, so in float char, bind one, wrap it in wrap type with std add pointer. So the second one will become a pointer. So float should become a pointer, and check if it's the same as int float pointer char, and then I tag assert on that, and it worked. So yeah, that's the end of my presentation. You can see my library at this address. It's version 0.5, since I need to do a little bit of cleanup, not a lot of things, just mostly function names, and make sure that everything is okay for the release of 1.0. And you can test it with Compiler Explorer using this include blah blah blah, the raw content of my of this file. Yeah, because it's a one file library. So yeah, that's my presentation. I hope you like it. It was quite a blast to develop, and there's a lot of compiler error that I needed to solve. So yeah, that's my library. Thank you for listening. I hope you like it. Oh, if you have any question, you can ask it in the chat, or I will go in somewhere else I will wander around this this chat room to answer everything. Thank you. Okay, so let's I think I have a question there. Good joke, Odin. Okay, what is the compile time impact of this machinery compared to the implemented in the same logic within Brigand? So Brigand use so Kvasir and Brigand are kind of the same family, and they use template alias mostly. Me, I'm not doing that because I realize that every single type alias goes to a struct, and so basically, the simple answer to this question is that Kvasir and Brigand have a lot more specialization based on their number of inputs that you receive at the same time, and so this is the reason they get faster. I was not aiming for that. I was hoping for a lot more expressionability. So you cannot write bind very easily in the other library, but very easily in mine. So my hope is that it's not as fast as Brigand or Kvasir or no, those two I can accept that they are faster, but not the others. and yeah, that's it. That's the simple answer. We can talk about type instantiation after that. I will be happy to answer, but I'll take another question. Why do you use so many underscore? Because I like it. That's as simple as that. And this is my library. I can do whatever I want. Okay, so how much compile time increase with more types involved? It depends on the question that you. It depends on the meta expression that you use. You quickly realize that some function like transform can be expanded, and it will not use a lot of instantiation. Like basically, a for each will instantiate all those meta expression inside the same result. So technically, the counter of instantiation will increase up until it gets to the final result, and then it will start from this number. There's not an easy way to respond to that. And yeah, this is not a question, and there's only 2 minutes left. I'll leave the podium to the next presenter, and thank you all. I hope you like my presentation.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.